Do that mini check. So systems. Now, kind of what's this all of a sudden? Well, basically, just about anything you can do with regular X and Y math, rectangular math, you can also do with polar math. And so when we talk about a system of equations, we're talking about like two polar equations. And when you have two polar equations, you're trying to find like the common solution. It's the intersection point. And so the slide you're seeing here could be the same slide you would have seen in an algebra class, because it's still true that the solution is just the intersection. You can write that down if you want to, or you can just kind of read it, because I'm sure this isn't the first time you've heard this idea, but we'll use it today. Solutions are points. That's pretty basic stuff, but I find sometimes that students forget when we get into polar math. So their solutions are points. Okay, r and theta. In other words, you need both. And then the ever famous solutions have to work when you plug them back into all the equations. So here's a classic little system. In case you're still trying to just remember what's a system, it's, again, when you have multiple equations solved simultaneously. Usually it's just two equations, but it could be more than two. It'll just be two for our problems. So we're trying to find the solution to the system. In other words, we're trying to find the r and theta that works in both equations. We're trying to find the point of intersection. And that's exactly what we're going to do using two methods. Yes, one of those is a graphing method. We'll do that first. And then the other one is like an algebra method. It's interesting to see which method you kind of like more. Actually, we'll ask you to do each method. So I want you to learn both, but we're going to do like a graphing method. Okay, now make sure that you can do this. You can watch, you can play along. It's not too hard, but when you have polar math, the idea of tracing can sometimes be a little different. By the way, did you catch some of my small hints on the online lessons? Do you know what these graphs are? Do you know that this first equation is going to be a circle? You'll have to study that little chart to just kind of remember that for the test. The second equation is of the form a plus or minus a, like both numbers are the same. That's always going to be trying to make a heart, having trouble. It's always going to be a cardioid. Okay, and again, you can study that chart to remember that. Okay, so where does a cardioid intersect a circle? Oh, and it kind of looks like a snowman too, perfect for this time of year. Where does the cardioid intersect the circle? Visually, you kind of want to see these 3 points of intersection. Again, visually, you want to see those because we're kind of like looking for, we're going to go in search of those spots. Kind of mathematically, we need to trace to those. Remember, to trace in polar math, you have to, in second zoom, change your calculator to polar GC. Second zoom is the format menu, switch to polar GC. Now when you push the trace button, you end up with r and theta, which kind of makes sense. That's what we're doing. The first point, the default sort of location there, is 0, r, 0, theta. So 0, 0. Now listen, I'm not going to give you one where the intersection points are strange. So, we get to a nice 2.5, 30. You don't have to wonder if it was like the point right before that. So we get to 2.5, 30. Now, when you trace to the right, that doesn't mean the cursor goes right. It just means it rotates. So when I trace to the right, I'm actually rotating. You want to think of it more like that, just like when you guys graph stuff by hand. That's why I had you graph stuff by hand a couple lessons ago. Okay, now, as you keep rotating around here, you hopefully realize that you sort of can contact those points again. So 0, 180. So negative 2.5, 210. So negative 2.5, 330. And then all the way back to the beginning. Okay, so I guess kind of what we're trying to point out here is there are definitely multiple points that seem to represent the same point. Sound familiar? Again, there are multiple points that seem to represent the same points. So we're getting quite a list here. Well, here's kind of the secret. Some of these, well, let me see how I want to phrase this. You have to check these points because there is the possibility that some of them may not actually be solutions. What do I mean? Well, if you plug 0, 0 back into these two equations, does it actually work? So if I plug theta equals 0 back into the first equation, I get 0. But if I plug 0 into the second equation, I actually get 5. It's kind of weird, but what I'm doing is I'm plugging the first point back in, and it looks like that I don't actually get it to solve the second equation. Okay, because simply the R value doesn't also equal 0. Yeah, it ends up getting crossed off the list. How about the next point? Make sure that you know what I'm doing here. I'm just plugging in the points, but that really means that you're plugging in theta. So I'm plugging 30 into the equation. And I got to plug 30 into both equations. And when you do, they both come out to be 2.5. Okay, good. That's kind of like what you expected to happen, right? You know, it worked. Now, I just want to encourage you to check like one more point. Just for time's sake here, we're not going to have time to check them all. But are you checking like at least one more point? Because if you are, you would discover that the next point also works. It turns out that the rest of these points do not. Now, don't make too many conclusions. I didn't say that the negative ones are never going to work. I didn't say that you only ever get two answers. It just turns out that for this problem, the only points that work happen to be those two. And so they make the final list. Are you checking something else? Do you have a question? Because I don't want to just say so. I want to make sure I show you if you need it. Just again, if you plug in 210, you are not going to get negative 2.5 for both equations. For both equations. That's why we crossed it off. Okay, now this was like a graphing method. Maybe you just kind of did it on your calculator. That's fine. Let me show you, though, the algebraic method. This will probably need to write some stuff down. And I kind of like the algebraic method because, well, it's a little more mathy. It doesn't mean that it's hard. It's just a little more mathy. If r equals 5 sine and r equals 5 minus 5 sine, then wouldn't it be true that both equations are equal to the same thing? Basically, a substitution method, a very simple substitution method, would allow us to substitute 5 sine theta in for one of those r's. And now we're staring at a little equation that we spent a little bit of time solving last chapter. Again, look at what you got here. It's an equation. It's got one function. It is solvable. Okay, it looks like I can gather some like terms, like add the 5 sine to both sides, and that will give you 10 sines equaling 5. it looks like I can divide by 10 and get myself down to sine equals a half. Now, I like this juncture because sine equals a half is a theoretical thing that I want students to understand. We are trying to do more in this class than just get answers. If you just want to get answers, you can probably find them on the internet or on a calculator. Okay, I get it, but I'm trying to teach you how to understand what this is. What I'm getting at is that this is a triangle, and maybe it's more than one, because when sine of theta equals a half, that's referring to the dimensions of a triangle with a y value that's positive. With the y value that's positive. When I draw this triangle right here, you shouldn't be shocked because it has a positive y value. But so does this one. Okay, now both of these triangles satisfy this statement. What you want to realize, though, is that the answer to this problem is not just a triangle. And the answer to this problem is not even just like 1, 2, root 3, but it's an angle. And this is like the theory of trigonometry, that you realize that we are in search of both of these yellow angles, because that's always what an inverse would do. Okay, when I do the inverse of a half, I would produce an angle. It looks like I'm going to get the angle that's across from 30, okay, because 30 is my reference angle. Again, it is a special triangle. I'm assuming that you're processing that, so we have 30 degrees here also. But of course, the other angle is not 30, but 150. Now, if you're looking over here, you're saying, oh, okay, yeah, we sort of found those angles. Yeah, we kind of already found it. But here's what you want to realize. Now that you have your two thetas, how do you write the final answers? How do you find the point? Think about this with me a second. I have half of my point. I have theta. How do I find r? Well, like you always do in math, you can plug back in. So I can plug back into either one of these equations, 30 and 150. So a lot of students plug them into both just to make sure everything's right. But it's right. You're going to get 2.5 when you plug it back in, which of course we kind of already found with that graphing method. Now, what I just showed right there is like what would be expected when you show your work for the algebra method. You obviously solve the equation, but then I want to see the triangle. In this case, triangles. I'm only going to give you one that is possible to solve like this. So it would have to have something with special angles in it. Systems. A nice little lesson with a kind of a connection back to some math that we've done before. And that's how this class works. We keep kind of going back to some other ideas. There's an exit ticket, but honestly, you're not going to exit. You're going to need to take it along. But there's an exit ticket that basically is 3 problems that are systems. It'll turn into like a homework, but it's a little turn-in tomorrow. It's a little turn-in. Converting. I know you kind of have to be thinking about some different things here. If you have a question about converting, because maybe from the practice that I gave you on Friday or from the homework, you may ask me. I'm going to just do it individually. Obviously, you're allowed to look at your notes, which includes the practice that you did Friday, as well as the homework. Okay, so again, if when you were home over the weekend, if you were like, I have a question about this kind of problem, ask now before you get into the little mini check.